Cool. Thank you for the introduction, Chaler. It's a pleasure to be here. Chaler is very modest. He said we were old colleagues, but he was actually one of my mentors who taught me some of the early when I started getting to working on recurrent models and stuff. And so that's what today, that's what I'll be talking about. Many of you might have heard of or be familiar with these state space models. And today I'm going to kind of give an overview of the bit of the longer line of work and some of the different variants of state space models and kind of some of the properties and how I think about them. So let's get started. So many of you are, as we know, we're seeing extremely advanced capabilities of all sorts of models today. This concept of foundation models that has started recently involves large pre-trained models that have extremely advanced capabilities on all sorts of modalities, from models such as text, such as the GPT series for text generation, to models such as for audio, images, time series, and more. And all of these models, one thing in common to them is that they are often based around very similar architectures, and in particular, these architectures are what we can call sequence models. And so the primitive that's in the core of these architectures is basically a very powerful sequence-to-sequence mapping layer that can operate over sequences of data or tokens. And no matter what sort of modality you put into it, this can lead to some of the amazing capabilities we've seen of models today. Almost all these models today are based on the transformer or the self-attention block. But really the way to view that is just what I call a sequence model, which is what I'll be talking about today. And so I'm going to define sequence model very narrowly using the following technical definition. A sequence model is just going to be a function that takes in an input sequence and spits out an output sequence. So we could just think of it as a parameterized black box or function. In this case, we're going to view it as basically just for the most part, we'll think of it as a one-dimensional to one-dimensional map. So as illustrated in this diagram. Now, with this definition, in practice, we might have a slightly more sophisticated definition, such as we'll often have a batch dimension and maybe a larger channel or model dimension illustrated in the top right here. But often we can basically just take the core of this is basically just a 1D to 1D sequence map, or that's going to be the simple case we think of today. And many different models satisfy this basic interface, such as older models such as RNNs. Nowadays, the most common one is self-attention, and other things such as one-dimensional convolutions or neuro ODEs. Lots of different types of models might satisfy this basic black box interface. I will also make the distinction between when I talk about sequence models, I am going to think about like these very core primitive building block layers, such as a linear convolution layer or a self-attention layer. And I'll make a distinction between that type of sequence model versus a deep sequence model or a deep neural network, where basically when we have one of these kind of primitive sequence models, it's just a black box sequence-to-sequence transformation, we can fit them into a more complicated neural network architecture that can involve different types of layers, including normalization layers like batch norm or layer norm. Often it'll have pointwise linear projections, residual connections, and so on. And these are composed into these end-to-end deep sequence models that express much more complicated functions, and that's what we use as a deep neural network. But the way that basically I think about them is that models such as a transformer basically is some sort of arrangement of these components, pretty much none of which actually model the sequence part except the core attention layer or the sequence transformation. Similarly, CNNs actually are very similar to transformers, and really the only difference is that the way that the neural network is wired together might be slightly different, but it's pretty much the same, and the only difference is that the core black box layer that mixes across the sequence dimension could be a convolution. Similarly, when I talk about state space models today, I'm going to think of this as a very actually quite simple building block sequence transformation, and we can incorporate it into a neural network architecture in much the same way as a transformer. And the holistic architecture we might call a state space neural network, similar to a convolutional neural network, or these are sometimes called SSM architectures or deep SSMs. So there's many ways of referring to this, but it's useful to make the distinction between kind of the end-to-end model versus the inner SSM, which is the core thing that we'll analyze. So I would be talking about state space models. More specifically, I call these structured state space models for reasons that I'll explain later. And so the first variant of these that was introduced in the literature a couple years ago is the original one is called just the structured state space sequence model, or S4 layer. And again, this is kind of a simple linear black box mapping. And then I'm going to move to the more recent variants, which many of you might have heard of, called Mamba. And the way to think about Mamba actually is that it refers to the entire neural network architecture. And I'm actually not going to talk much about the whole architecture because the core inner layer is going to be, again, this core state space model, which I call the selective state space model. One kind of interesting theme about all of these, which hopefully we'll get to today, all of them today, is that this broad class of what I call structured state space models, or just SSMs for short, are actually broadly related to all of these classical families of sequence models. And so I view them as this pretty fundamental and deep modeling layer that underlies and unifies a lot of the other ideas that have appeared for these other ways of modeling sequences. Okay, so finally, we are going to think of, for a specific use case, we are going to focus on autoregressive modeling. And so here is kind of what illustrates the process, which is where we're going to try to model distributions of sequences. And we're going to kind of think of the generative model setting where we're going to generate these sequences by doing this autoregressive prediction, where during train time, we're going to have the model predict the next, learn how to, given some context, predict the next token. During inference time, it's going to generate sequences one token at a time by feeding them back in autoregressively. So hopefully we're all kind of familiar with this, which is the way that GPT and like language models work as well. Although they can be used in other modalities, such as audio here was actually another place where they were very popular. One thing that's just useful just to tie things back together is that I defined a sequence model as this sequence-to-sequence transformation. And this looks very different than this kind of like unrolling one step at a time prediction. But actually, the sequence-to-sequence mapping is still the same interface that we need at train time. So to train this sort of model, just to recap, you feed in an entire sequence at once, and then your model is going to spit out, you pass it through this black box function, you get an output sequence, and every single element of the output we view as representing the model's prediction of that, the model's prediction of its guess of the next token, given all of the previous history. So as long as you have, here we actually need a causal sequence-to-sequence model, which means that the output at time t depends only on all inputs up to time t. And then using this black box sequence-to-sequence transformation, we're able to do autoregressive modeling. And that's why kind of just thinking about this interface is sufficient. And so we're going to just kind of stick to this very simple definition. Okay, so let's look at some classical types of sequence models, just so we have we're all have the same background. So up to the advent of the transformer a couple years ago, the RNN, or recurrent neural network, was kind of the canonical sequence model. And it is actually maybe the most natural type of sequence model that naturally models input in a sequential dependency. So the way RNNs work is that this is how they used to be illustrated. Basically, there's this black box function, which is called A in this case. This function basically consumes an input for the current time step, as well as the previous hidden, the RNN maintains a hidden state. And then it's defined by this black box function that combines its previous hidden state with the new input to create a new hidden state. And so basically, it's this recursive update function. And this is maybe the most natural way of modeling how a sequence evolves over time. And so before transformers came, this was pretty much the only way people did it because it's the most obvious thing to do. And so it's kind of characterized by being the sequential model. And this gives it it's kind of characterizes its strengths and weaknesses. So its strengths are that it's very natural for modeling causal sequences. And it actually has very strong inductive bias for sequences. So it's very good at some applications. It's very data efficient in some settings. And it's very efficient because you can do, say, autoregressive modeling very efficiently, where every single time you generate a next token, you can feed it back in and just apply your same function again and again. And this is always going to be a constant time at generation time. The downside is that even though it is kind of natural and very efficient at inference time, it is slow to train on modern hardware because of these sequential dependencies. which is not parallelizable like on GPUs. And it also runs into some optimization issues or modeling issues, such as this well-known problem called vanishing gradients, which was well studied several years ago. So those are RNNs. And then the other model we're going to focus on are transformers, or more specifically, transformers are kind of characterized by the self-attention layer. And these are characterized, just like RNNs are characterized by being sequential, transformers are characterized by almost being the opposite, where they're kind of they're modeling dense interactions. So as we all know, the way attention is defined is that it looks at, you have a sequence of data, and then it basically looks at every single pair of positions and looks at all the pairwise interactions. And once again, this characterization informs its strengths and weaknesses. So its strengths are that it performs very well because it's doing a lot of work in comparing every single pair of tokens in the data. And that's also very parallelizable, so it's efficient on hardware. And then its downsides are that because it's looking at so many comparisons, this is what they call the quadratic bottleneck problem, where it scales quadratically in the sequence length. And similarly, at inference time, it scales linearly in the sequence length, which is, so it gets slower and slower the more data you see. And that's kind of not desired. Okay, so those are sort of the background models. And so we're going to build up to Mamba, which is going to try to combine the best of all worlds here. So we are going to hope to be able to come up with models that are very efficient at both training and inference. We want it to be linear time during training, scaling in the sequence length. We want it to be parallelizable on GPUs, and we want kind of a fast inference, in particular, hopefully constant time inference. And we also, of course, need strong performance. The holy grail here is that we're going to kind of focus on language modeling, where nothing is really matched transformers until these sort of models. And you can start doing very interesting capabilities, such as with both efficiency and performance, you need both of those to unlock new capabilities, such as being able to really model long context, such as handling very long sequences requires you to both be efficient, have efficient scaling in the sequence length, and actually be doing and actually be able to model the dependencies happening in this very long sequence. And so Mamba is going to take a significant step towards this. Okay, so that's kind of the whole background section of this talk, just setting up the sequence models and some of the baselines. And so the rest of this talk, we're going to first talk about the original type of structure space models, which are also what I sometimes call the S4 variant of SSMs. And then we'll move into the Mamba variant of SSMs, and then talk a little bit about empirical performance. Okay, so let's just first define what these SSMs are. So they're defined by these two equations right here, and often illustrated with some sort of control diagram, because these models originally came from other fields of science, such as control theory. And the first kind of version of these models that was kind of used in this modern form was the Kalman filter from many decades ago, and is still commonly used today. So the equations that we'll use are kind of the same. They share the same equations, although as we'll see, they're used in very different ways, the way we'll be using them. But they're basically just defined by these two simple equations, and you can view them as a linear differential equation. So in 1 second, we're gonna unpack how to think about these. But the way that we're going to think about them is actually, even though they share the same equations as the Kalman filter, what I call the structure state space models are kind of more specifically, when I say SSMs, I will refer to these models, and I'll explain why later. But these models refer more narrowly to a certain class of models that we're going to use in deep learning that includes things like S4 and Mamba and so on. And these models are, we think of them as deep learning models in the same way that I previously defined, that are broadly related to these classical SSMs like the Kalman filter, but actually more closely related to other deep learning models such as RNNs and CNNs. And they have many properties, as I mentioned, that kind of connect a lot of these models. So now I'll kind of go through some of their properties and how they relate to all of these. So as I mentioned, the way that we're defining sequence models are black box functions that map one input sequence to an output sequence. And again, in deep learning, we use these black box functions that are parameterized by some parameters represented by theta here. And in this case, for an SSM, these theta parameters are the A, B, C, and D matrices that we just saw. And given this kind of a black box mapping, you can compose them into a much more expressive parameterized function. And then in deep learning, we're going to just hope that this can learn whatever desired transformations we care about, and we'll learn the whole thing end to end with gradient descent. And so in deep learning, we're not going to think about the whole gradient descent process. We're just going to think about the main problem is how expressive is our function, and can we compute that function fast enough to scale? More narrowly, I call these more narrowly, if I really want to differentiate older SSMs such as the Kalman filter from modern SSMs such as Mamba, I call these state space sequence models because we're going to use these in using this black box definition the way I define a sequence model, which is different than how many of these other fields think about SSMs. Now, actually, so instead of just a sequence map, one thing that is already different from about these SSMs, given the way I define them, is that remember they were defined using differential equation, and so actually you can view the domain of this function as continuous time, and instead of mapping a sequence to a sequence, we can view these models as mapping a function to a function. So we can think of this as taking an input function, say x of t is a one-dimensional function. T is the time axis, x of t is this function, and we're going to think of this as a black box mapping that spits out an output function y of t. Okay, and so how does this mapping work? So here are the equations again. So let's kind of step through how exactly to think about these equations. So okay, so these equations in total, again, are going to we're going to think of it as a black box transformation from this input sequence x of t to this output sequence y of t. And now these two equations are going to factor it through a latent state. So the first equation is going to take the input to a higher dimensional latent state called h of t. Now we're going to think of this as a higher dimensional state with n dimensions, where n is going to be kind of a tunable parameter that you control. And we'll think of this as on the order of, say, 100. So this first equation we're going to think of as mapping this input function x of t, which is 1 dimensions, to a function h of t, which is 100 dimensions. And this mapping occurs by first there's this b parameter, which kind of blows up your input from 1 dimension to 100 dimensions. And then the dynamics of this equation are controlled by this A matrix, which is a square matrix that controls basically so this is going to be a linear ordinary differential equation where the dynamics are controlled by this transition matrix. And so given this equation, given any input x, there is going to be a unique solution h, which is going to be a higher dimensional function. And here it's illustrated in these blue lines, although here we're only illustrating 4 dimensions. And then the second equation is going to take this higher dimensional function and project it back out to 1 dimension. So, and this one is going to operate pointwise, and so there's no kind of mixing across time here. The c parameter is going to be, you can think of it as a row vector that given your 100-dimensional state, you have a 100-dimensional row vector that just kind of projects it back down to 1 dimension. Or you can think of this as the c parameter. You can think of as a sequence map, you have these 100 blue lines here, and we're going to take a linear combination of them controlled by c to give me my output y. And we often define these also with this little d parameter, which is just a scalar that we can think of essentially as a skip connection. Or you can think of d as being 0, so you can ignore it. Or when d is 1, you can think of it as a skip connection that just adds back the input there. And in terms of the theory of these models, we can basically ignore this because it isn't really, again, affecting the whole sequence map. Okay, and so that's all these two equations are. So as a whole, these two equations define a map from an input function x to an output function y through this higher dimensional latent state h. So they're actually mechanically quite simple. And this already kind of completes the first property that I was going to mention. So first of all, these models, these structured state space models are different from other types of sequence models because they're actually defined in continuous time instead of discrete time. And this is something that distinguishes them from a lot of other models and can give certain this type of this flavor of the SSMs different types of properties. For example, these operate really naturally on data that looks kind of like continuous signals. So this is just a question of inductive bias. If you have data that's very smooth, things like, say, audio waveforms, then these models have very strong inductive bias for it and can model them very well. much better than other models like transformers. And that's all because they have this implicit and continuous time representation. Okay, so now we're going to talk about the other representations, which are actually about computing the models. So I kind of previously I defined this as kind of a one thing that's useful is to distinguish that these models, we're thinking of them as functions. We've defined the functional transformation of how do you what is the functional definition of the input to the output. But the next representations are going to be about how do we actually compute this transformation. And this is one of the main problems we care about in deep learning. And so the first way to compute them is going to be kind of the naive way of computing them, where we're just going to unroll the models one time step at a time. So we had these two equations of the SSM, and the first equation is the one that actually controls how does it evolve across the sequence dimension. And so this equation was defined using a differential equation, but we can actually think of it as kind of you can basically turn this into a linear recurrence, where I'm not illustrating it here, but through a process called discretization, we can turn this equation into a very simple linear recurrence. And basically, we'll just say that every single time step, we get a new, and we'll, just like RNNs, we're going to look at this one time step at a time. We get one new scalar input x, process it through this recurrence by multiplying it by b, combining it with the previous hidden state, where it's multiplied by a, and then basically just adding them, and then that gives me my new hidden state. And so we can basically, like ignoring the entire output, we can basically take the input one time step at a time. And then using this equation, we can evolve the hidden state using basically the simple linear recurrence. And then using the second equation of the SSM, we can project that hidden state back out to the output. And so this is kind of, so you do have to do this thing called discretization, which is actually quite simple. You can basically just use these fixed formulas to transform this equation, which I'm not illustrating here, but this actually is a very simple way of viewing the model. And so we can basically view these types of models as essentially, instead of state space models, some people like to think of them as basically linear RNNs, which is kind of another way of characterizing them. And the reason why this is really important goes back to the efficient inference that I talked about. And so just to kind of relate this back to the whole functional viewpoint of these models, let's think about what this model is doing as a function transformation. So again, the SSM is going to be a transformation from this input to an output. Let's say we have sequences here, so input sequence to an output sequence. And now let's examine the autoregressive setting, which is where suppose I've seen some prefix of my data. Say here I've seen, this was generated from real data. So we've seen 8,000 data points. And now I get one new data point, and I want to compute the next output of the sequence. And in the SSM, we're going to basically take that new input, implicitly evolve a new hidden state, and then project that hidden state back to the new output. Now, but if we're thinking about this from the functional point of view, I'm taking a new input and generating a new output, but this new output actually depended on the entire history of my sequence. So as a function, we're basically saying there is some function that is going to take this entire prefix and compute like this one new output number, right? And this output really depends on the whole thing, which means that the time it takes to compute this should scale with the length of my input. And that's how long it takes for most sequence models such as transformers. But with recurrent models such as SSMs, we can compute it in constant time because of the fact that we can factor this whole transformation through this hidden state. And so that's kind of one of the reasons why these models are so important, because this is the only way that you can really do kind of like, say, real-time streaming applications or online processing as your context gets longer and longer. And this is not true for many other types of sequence models we might care about. And so this is the second property or representation, which is that we can write the models as basically a linear RNN. And this lets them be computed in a certain way. And this particularly lets them be computed very fast in online settings, such as if we're doing generation with an autoregressive model. And finally, the downside of this is that the same downside as normal RNNs. So the recurrent representation was useful when we're seeing the inputs in an online fashion. In the previous animation, we saw the inputs one at a time, where they're kind of being revealed to us one at a time, just like if we're using like a GPT-style model to generate. But during training time, we actually see the entire sequence at once. And we see kind of all the future data points, so we're not constrained to processing this sequence one at a time. And so in this setting, these models, computing it like this actually suffers a lot from speed issues during training time on modern hardware such as GPUs and TPUs. And so this is one main problem. And there's actually a second problem that's kind of a more subtle, but also more fundamental, which is that the way I define this model is that I'm taking a one-dimensional input and outputting a one-dimensional output, and I'm factorizing it through a latent state. And this latent state is much bigger than the dimension of my input and output, which is actually what gives these models much more expressive power than older RNNs. It's the fact that the latent state is a higher dimension, which is a theme that we'll touch on later. But the issue is that if I want to compute this latent state, then I'm going to have to, because it's 100 dimension times bigger than the input or output, I'm actually going to be consuming basically 100 times as much memory and computation as it takes to just store the input and output, which is going to be basically a real big issue in deep learning when in deep neural networks when I need to do this really fast, and I'm kind of I'm basically bottlenecked by the computation time of processing the input and the outputs. So it basically turns out that naively computing state space models by kind of materializing the latent state and then using the way that we kind of define them is completely infeasible in deep neural network. And so this is one reason why these models were never used until kind of recent work. And so one of the main challenges is figuring out how to get around this bottleneck. And now in the type of model that I've defined so far, the way that we do it is by using a very clever rewriting of the entire model. So this is what I call the convolutional representation. And the idea is that we're computing this function as always. And the function really what we cared about was the map from the input to the output. And although we define this function as being factorized through the latent state, it turns out that there is a way of a completely different way of computing it that avoids materializing the latent state. So basically, there is a different way of computing the model that still produces the same function. It still gives me the same map from the input to the output, but avoids the state. And the reason is that we can completely rewrite this model into the form of a vanilla convolution. So what does this mean? So basically, so instead of computing that blue latent state, we're going to first take our parameters of the model. So here the parameters were A, B, C, and D, and actually just A, B, C are the important ones. And given A, B, and C, we can define what I call the SSM convolution kernel, which is this green sequence or function that I call K for a kernel. And so this is uniquely defined as a function of the parameters A, B, and C. And then given this kernel, I claim that basically the map from the input to the output can be viewed as a straightforward vanilla causal convolution between the input function and this convolution kernel. Now, what I mean by a convolution is that kind of, as this illustration kind of shows, you think of it as the same way as a normal convolution, where you take the kernel and you take your convolution kernel or a convolution filter, you slide it along the sequence, and every time you slide it, you kind of take the dot product with your input, and then that gives you the corresponding output at that time. Now, the only difference from what you normally think as you normally view convolutions as is that the convolution filter here is actually as long as your entire sequence, and actually it's implicitly infinitely long. But other than that, it's actually the exact same definition as your normal convolutions, up to like padding. Now, the other reason why this is important is that these convolutions, I kind of define them as you take this kernel and you slide it along every position. But actually, if you think about it, that would be way too slow. Because yeah, that would actually scale quadratically. But it turns out that you can still compute this entire function in nearly linear time using well-known techniques from signal processing. In particular, the fast Fourier transform gives us a way to compute this whole convolution in almost linear time with an extra log factor. And so this provides a completely different computational pathway to go from the input to the output that scales nearly linearly in the sequence length and avoids materializing that hidden state, which was, as I said, was computationally infeasible. And so as another kind of like high level point, this is for these original models, this is, I think, maybe the most useful way of thinking about these models. I found it more useful to think about them as convolutions than as recurrences, because you can kind of think of them as a linear transformation, just like CNN, like convolutions in a CNN. And you can think of these as being a variant of a CNN or almost a generalization of a CNN, where the convolution kernel is actually infinitely long, which is one of the reasons that gave these models the ability to process long sequences, as well as the fact that the convolution kernel is actually implicitly defined through your smaller parameters A, B, and C, rather than being explicitly defined by modeling each time step. Okay, so that was the final representation. And so, as I promised, these models are also related to CNNs. They're related to RNNs, and they're defined as these kind of using the same equations as these classical SSMs in continuous time, which gives them the ability to model lots of interesting data. And concretely, we'll leverage kind of all these representations, which is why these models are so interesting, because they have all these interesting theoretical connections. And in particular, as I mentioned, during train time, we'll use this representation because it's faster at train time. And then at inference time, if you want to do online processing, you can switch to this computational mode. And as I mentioned, there's actually more capabilities you can do because they're continuous time, such as adapt to different resolutions and so on, but they're also just very good for continuous data. The way they're defined makes the kernels actually implicitly decay, as you can see here. So the effective context range might be different. And there's a lot of theory you can do to kind of control how long you think this kernel is, and you can analyze what's the expressivity of this kernel. There's a lot more there, but sure. So basically, in the limit, you actually can get arbitrarily expressive kernels, but in practice, these have certain inductive biases that kind of have this decay.
There's some trade-off kind of thing, right? You principally could model everything in the past, but then you have to process everything in the past too.
Yes, that's right. So actually, this is going to kind of cover more of the trade-offs we'll see next about kind of the more fundamental, like the fact that, I mean, this is touching on deeper topics. So you're kind of talking about how even though this kernel is infinitely long, it actually is constrained in certain ways. For example, here you can see that there's certain types of exponential decay here. That itself is a function of the fact that this kernel is defined using this compressed representation A, B, and C. And that's also deeply related to the fact that in the recurrent representation, although I'm getting this kind of inference speed up, there's actually still kind of an information bottleneck because I have a finite hidden state. So even though I have a function that is like much faster to compute, that's necessarily going to be kind of more constrained in its representation power. And these are all related concepts. So yes, these are more subtle, so it's hard to characterize these theoretically, but that's kind of the trade-off of these models. But at least kind of from a computational and kind of like a intuition perspective, this is how you can kind of think of them. How do they relate to these other models? And we'll kind of touch on their other trade-offs later.
One question that I have related to this information bottleneck that you mentioned. So in my understanding, one of the reasons why RNNs got replaced was the finite dimension of the hidden state, that maybe it wasn't always expressive enough, right? So you either have to like blow up the dimension, or just replace them with something that attends to all of the previous inputs, right? Like that mechanism does. And so, what's your intuition here? Like, when SSMs are sort of like a revival of RNNs, and in a way, like, do they still suffer from the issue that the hidden representation is sort of limited in what it can express, or you can overcome this somehow?
Yeah, so I think there are some fundamental you can call them limitations of basically these sort of recurrent models, where there are some things they fundamentally can't do. That's actually, I think, a more kind of a high-level topic that we can chat about afterwards. And it's actually more related to the next part of the talk about Mamba. Yeah, so you can't represent, because of kind of this finite bottleneck, you can't, in practice, like kind of represent everything in the past. Now, a lot like you might view these as limitations, but actually, you can also view these as kind of strengths or inductive biases, and it's kind of actually exemplified by these whole properties. So, for example, I kind of maybe hinted at earlier that if you have data such as audio waveforms or like very smooth data, transformers are very bad at modeling that data. And one reason is actually the fact that you can turn this on its head and say that the reason is because these models have a bottleneck that's compressing it. And so kind of the point is that when you have data such as like a smooth signal that's very compressible, you actually can represent kind of the information needed to like represent that sequence through a much smaller bottleneck that kind of can store that information you need. And so by constraining your model to have a smaller bottleneck, it's actually doing feature learning in a way that's better suited for the data compared to other types of models that are actually like, if you take a model like a transformer that's trying to remember every single time step, and you try to throw at it kind of this like smooth data with lots and lots of very compressible information, then that's actually a bad thing. So there is this fundamental trade-off, which I'm about to get into in just a few slides, where these models, we think of them as doing very different things from a transformer, and that gives it certain trade-offs. It's both a weakness in some cases and a strength in some cases. So here, with this family of models, they're most suited for kind of continuous data, and another way of thinking of continuous data is as highly compressible data. Because when it's continuous, like every single new data point is kind of information constrained because it's going to be close to the old one. And when your data is very compressible like this, these models are actually much better than this is where they kind of excel. Now, I'm not going to say too much about this because there's actually a lot of like interesting things we could say about it. This could fill its own kind of an entire kind of a subline of work on models for modeling things such as audio and video at high resolutions and what makes them work there. And there's also a lot of interesting theory you can say about them for kind of proving what sort of representations they learn. So a lot of this line of work came out of this earlier framework called Hippo, which was about exactly this question of assuming I have a model like an SSM that has this finite state that's evolving through time. This state represents everything that the model has seen so far. And can I provably construct SSMs that are learning states that are capturing certain features of my entire history? So Hippo was about this question of like, given if I see this sequence online and I'm compressing it into a finite representation, can I provably reconstruct the history of the sequence I've seen so far in some interesting way or adhering to some constraints? So I won't go too much into this, but yeah, there's a lot of interesting previous line of work that came out of this, and still a lot of interesting theory that you can say for certain settings where you might care about these problems. Okay, so I just want, before talking about MAMA, I just want to focus on two key characteristics of this type of model that I've talked about so far. So the models I've talked about so far have had these ABC and mostly the ABC parameters be constants through time. So in particular, these things are not changing as my time evolves left to right. This parameter is always the same parameter. These models are called linear time invariant models because the parameters are invariant through time. And this whole transformation is going to be a linear transformation in the linear algebraic sense. We'll sometimes just call there's lots of derivatives of these models that can focus on either the convolution or the recurrence point of view. And sometimes I'll just call them linear time invariant SSMs just to distinguish them. Now, the second key characteristic that I've kind of alluded to, and here I've illustrated it in various ways, but here I'm illustrating it using the control diagram, is the idea that we had like this 1D input X to a 1D output Y. It got blown up through a column vector into a larger hidden state. This hidden state kind of evolved using this recurrent dynamics that, and in control theory, to call this like a control loop. And the point that one of the key things I talked about was that this hidden state is a larger dimension, like it could be 100-dimensional, even though the input is 1-dimensional. And I mentioned that this is infeasible to compute for deep neural networks. And we need to avoid, one of the key characteristics of these modern deep SSMs is that we can never materialize this hidden state. And so the linear time invariance, the reason it's useful is because that is the exact thing that let these models be equivalent to the convolution, which let us avoid materializing this hidden state. Okay, so these are kind of the main concepts that would distinguish this family of models that I call like the S4 variant of SSMs from the Mamba variant. One final thing I'll mention is that just because I was told that many of you might have different backgrounds in, say, in engineering or other fields, state space models are a term that has cropped up in many, many different fields of scientific fields. So as I mentioned, they've this type in this form, they first cropped up in control engineering, and they're heavily used in, say, computational neuroscience, engineering, statistics, and so on. And in fact, this term is very loose and kind of non-descriptive, because what is a state space model? It's just anything that has a state space that evolves through time. And basically every single subfield of science kind of has its own version of state space models. From controls has the Kalman filters. In reinforcement learning, you might think of like these Markov decision processes or these state transitions as a state space model. Similarly, in robotics, they have different types of state space models. Computational neuroscience, and even machine learning before these more recent types of SSM. But people often are now using SSMs to refer to models like Mamba. But before all of this, when you think of SSM, you would think of models like hidden Markov models, which are entirely different than this type of SSM. So, and so I've defined, and even in deep learning, you might think of these differently. So in deep learning, we might think of SSMs now as kind of like Mamba, like autoregressive sequence models. And so I just think it's worth pointing out this distinction just so people across fields can communicate better. And so I've been trying, sometimes if I really need to distinguish this, I'll call the type of SSM that I defined, such as the ones with these three properties, as a state space sequence model, because they're used in that kind of sequence-to-sequence mapping, this technical way that I've used defined a sequence model for deep learning. And then, and I've kind of been really calling them structured state space models. So this is the term that I've preferred using nowadays to really distinguish these models. So the full way to define it is that they're structured state space sequence models, or S4. The reason is that I've left out a bunch of other details in the theory here where the state transition matrices of these models actually have to be constrained or structured in certain ways to compute these fast enough. I won't get into the details of why, but basically you can take my word for it that any types of these models used in practice have this additional structure imposed. And so I call them basically structured S4 models, or for short, structured state space models, or for short, usually I'll just call them SSMs, but with the common understanding that it's referring to this type of SSM and not like any of these other types. Okay, so I'm gonna go straight into the motivation of Mamba and kind of how they differ. I think we actually have some time afterwards to generally chat, so maybe I'll actually defer questions just so I get through all the material. Okay, so this relates to a theme that has come up in a few of the questions about the representation capacity of these models. Now, so I kind of define a bunch of these different types of sequence models, and they're all defined extremely differently. But one useful way I have for viewing these models is basically thinking about how to think about their trade-offs. One very useful way of thinking about it is kind of looking at what is their state representing. Now, and more specifically, their autoregressive state. Now, what do I mean by this? Basically, we can think of any autoregressive generative model as a type of state space model in the sense that there is a state which is just defined as what the model is storing in between time steps. So let me illustrate this by revisiting the old models we've seen. And so concretely, what I mean here is that let's say you have your GPT model or whatever that's generating your words or tokens. Between one token and the next, the model is going to store some information in memory that's going to facilitate it generating the next token. And that is going to be the definition of the autoregressive state of the model. Okay, so previously we looked at RNNs, which we said is characterized by being sequential models. And we looked at attention, which we said is characterized by looking at all the dense interactions of the models. Now I'm going to flip this and actually recharacterize these models through the autoregressive state. So the the RNN, instead of saying that this is defined by being the canonical sequential model, I'm going to now say it's defined by being the canonical model that uses fixed size state vectors. So, so previously I defined the hidden state, the autoregressive state, as whatever the model is storing in between time steps. Here, the model is the hidden state illustrated in blue is just this hidden vector that's passed in between one time step and the next time step. And so the RNN is basically always going to be maintaining a fixed size hidden vector. And then on the next time step, it's going to, again, take the new input, combine it with your hidden state, and produce the new hidden state, which is what's going to be persisting in memory to the next time step. Okay, and so by looking at what the model is storing in its state, we're going to redefine RNNs as models that are characterized by having a fixed size vector. This means they're doing very strong compression of the history of the data. So this is going to, once again, characterize the strengths and the weaknesses of the model. The strengths of the model is that at inference time, these models are very fast because they always have a fixed size state. And so processing one new input and combining it with the fixed size state is very efficient. So that's going to give you the constant time online or autoregressive inference. And this also explains why these models have the downsides, which is that they have difficulty modeling information-dense languages or modalities such as language. Because in language, you might really need to kind of remember everything that has appeared previously. And because these models have a fixed size state, it's difficult to compress all of that information into its state. And previously, we looked at transformers, and now once again, I'm going to recharacterize them as being defined as, instead of being defined as the model that looks at dense interactions, I'm going to define them as the model that caches the history of the model. And so what does this mean? When I have one new time step and I want to compute attention on it, I need to, because of the way attention is defined, I need to take that new input at this time step here and compare it to every single previous input. And if I'm doing that, then that means that I actually need to just remember all of my previous inputs verbatim so that I can compare my new input with all of them. And so in attention, there's this concept called the KV cache, which is how this is manifested, where we're literally going to cache a vector for every single previous time step seen. And so we're going to think of this model as doing as literally caching the entire history with like basically no compression along the time dimension. And so this is actually kind of the exact opposite of an RNN. And once again, this tells us the strengths and the weaknesses because by caching the entire history, this model kind of has very strong performance. It has access to all the previous data it's seen. It kind of can do long-range dependencies by just looking at any previous data point. And this exactly also explains why it's inefficient, because it has linear time inference, because it has to cache like every single, it scales with the length of the sequence because it is literally caching everything along the sequence dimension. And that exactly also is why it has quadratic time training cost. And so this is a very useful way of kind of illustrating what are the trade-offs of these models. So once again, attention is the model that does no state, it's characterized as doing no state compression, which gives it strong performance but poor efficiency. And recurrent models such as SSMs are characterized by having strong state compression into a fixed size state, which is why they have high efficiency but lower performance. And so to really move beyond these models and try to get the best of both worlds, we can look at the limitations of either of these point of views and think about what it takes to improve them. So from the attention point of view, which is once again caching the entire history, that is really wasteful, because what if we don't want to represent a vector for every single previous token? What if we have some earlier tokens that are just completely useless? Or what if we have some earlier tokens that are highly compressible? Then we really would like to compress this previous information into a smaller state that filters out irrelevant stuff and only remembers the relevant information. And from a recurrence point of view, such as for state space models, we want the state to be as expressive as possible if we're dealing with information-dense data. So first of all, we need the state to be large. It needs to be large enough to remember any information that's relevant that we care about for the task that we care about. And we need the state to store exactly the information we want, which means that our update function needs to be expressive enough to kind of do exactly what we want, and like remember the information that we need. And so that kind of motivates the selective state space model, which differs from the previous models that we call the linear time invariant models. Remember that those are the ones where the A, B, and C parameters were constants. The issue with that is that the second point where the combination function of how do I take my previous state and update it to my new state was too constrained. And so if I want finer grained control over how do I kind of process my inputs, I need to have more expressivity there. So this motivates the selection mechanism, which is a very simple difference where basically the A, B, and C parameters are going to be functions of, instead of being constants, they're going to actually depend themselves on the inputs. And this is going to give the model the expressive power needed to say whether or not they want to kind of pay attention to new inputs or say select new inputs versus ignore new inputs. There's a bunch of synthetic or like kind of like case studies or synthetic tasks that make it very obvious why kind of like when and why does this difference make a big difference in kind of performance. And there are certain tasks that it's very obvious that the linear time invariant models can solve, but linear time invariant models can't solve, but the selective models can solve. So I'm going to skip over this, but this is kind of all stuff that's in the Mamba paper. And that kind of motivates why we wanted the selection mechanism, which is basically just making these parameters depend on the input. Now, the only other thing, so basically the difference between the S4 style models and the Mamba style models is very simple. But the hard part actually of all of this is making the model efficiently computable, which I mentioned is one of the main things we care about. Now, this is another view of the whole thing where basically we have these one-dimensional input to one-dimensional output map that gets blown up through this B matrix to this larger hidden state H. And this hidden state H undergoes some like recurrent dynamics. Now, I mentioned previously that I emphasized that why did we need linear time invariant models? Because this hidden state H, I also mentioned that one of the key ingredients to make these more expressive is that the hidden state needs to be large, right? The hidden state needs to be large enough to remember information that we care about. But if we have this large hidden state, I kind of emphasized before that we are not allowed to materialize the state because that is going to be too slow. And so this is one of the main bottlenecks for making this model actually work for the new deep neural networks. And that's the reason why we actually made this constraint of linear time invariance, which was kind of a trick to allow us to avoid materializing the state, which is illustrated in orange here. And we avoided materializing it by using a different computation path using convolution. But the key is that we just can't materialize it. So now that we've made these selective, or we've made these like A, B, and C matrices depend on the inputs, the issue is that we still can't materialize this, but actually, unfortunately, in some ways, we're forced to materialize it. Unlike the LTI models, we no longer have this convolutional view that can avoid materializing the state. So we're actually going to need to take the input sequence, blow it up to this larger hidden state, and then project it back out to the output. And here we're going to use basically kind of like implementation tricks to do this efficiently, where we are still going to implicitly materialize it, but not in the location in the GPU that is expensive. We're going to materialize it in kind of a more efficient, ephemeral part of the GPU. So this is kind of occurring at the intersection of algorithms and hardware. And so we call this kind of this hardware-aware model that does this state expansion implicitly through a clever implementation and like knowledge of the actual hardware. And so in this talk, we care more about kind of the algorithmics and like modeling side. And so we're going to skip the details here. But in general, this is a very important area to pay attention to in modern deep learning is the interface between algorithms and hardware efficiency. And so the only difference between the previous linear time invariant or S4 type of models and the selective one is this basically parameter dependence. You can basically track exactly how it differs algorithmically. We sometimes call this, I mentioned that Mamba is actually an architecture, but the inner layer is this core SSM layer that we call the S6 layer for short, because it is like S4, but with this selectivity, and it's computed differently. Instead of using convolution, we compute it using what's called an associative scan. But often we'll just kind of conflate this with Mamba and say that this is just the Mamba algorithm. And so this is kind of the key takeaways. Basically, the motivation was about what is being represented in your state. We want the optimal trade-off between a smaller state, which is more efficient, versus a large state that's more powerful. But we want to compress information intelligently into our state, or compress it selectively. And the selection mechanism kind of allows much more expressivity and content-independent reasoning. And we needed to compute it using implementation tricks. I'll just say I'm basically out of time, so I'll just say kind of maybe like with the last 2 minutes, I'll just talk a little bit about some of the empirical results. Most of these you can find in the original papers, so I don't need to go into too much detail. But one thing I kind of wanted to convey is that there is kind of no free lunch in models. So there's many types of sequential data, from text, which is what language models are about and what a lot of machine learning cares about right now. And I view this data as very discrete because your text data comes in the form of discrete input tokens at discrete time steps. And there's other types of data that is also quite discrete, such as, say, modeling DNA is very similar to modeling language, but with a different alphabet. Now, on the flip side of this is a lot of types of data that look completely different than text. For example, audio, as well as things like time series and video, actually can be represented using a kind of more continuous, both in the time and in the data axis. So your data points are kind of any real number, and your time is also, in some sense, any real value time, right? So you kind of have this continuous data that looks completely different than text. And the point is that you can't use the same models to model both of these things, including the SSMs kind of very naturally are split between what they're good at. So for this type of continuous data, the original type of structured state space models, such as that previous part of the talk with S4 and many, many different variants of these are all good at modeling these sort of things, such as video and audio, but they're not so good at modeling things like text. And conversely, the Mamba variant of SSMs, as well as many other types of related recurrent models that have been coming out, such as XLSTM, DeltaNet, RetNet, and so on. These are much more similar, RWKV, these are much more similar to Mamba, and these are good at modeling things like text. And as a heuristic, basically, anywhere that attention is good at modeling, such as text, Mamba is also good at. And anywhere convolutions are good at modeling, such as images and audio, that's where the S4 or the LTI variant of SSMs are good at. There's lots and lots of experiments that have happened over the course of all these models. For these sort of data, there's the S4 paper has a bunch and many follow-ups. And the Mamba paper showed kind of a bunch of synthetic tasks where it showed that it can model million-length sequences. The most important ones were these scaling laws on language, which is why people really cared about these models, because these scaling laws are basically a way of validating how does your model scale with size and data. And nothing had really matched a strong transformer until Mamba, where basically a very modern transformer such as Llama is illustrated in orange here, and it basically, you can see compared to other models, it always has better perplexity and it scales better with larger model sizes. And Mama was the first kind of model that didn't use any attention at all, that competed with strong modern transformers, including on some of these downstream evaluations, which I guess I won't go into the details here. Something else is that these models, one of the things that I think are most exciting is that these models are not only good at language, but many other types of data that the community has started caring about more. So for example, DNA foundation models has become a more and more popular topic. Just like we have foundation models for language, we can try to have foundation models for genomics. And when we start looking at this different type of data, where you can view it as a different type of language modeling, but that using a different type of language that does not co-evolve with the transformer. And if you try to use these models out of the box on new types of modalities, what we found is that Mamba often works better than transformers out of the box. For example, on DNA, it works better than these modern transformers significantly. And as I promised, you can do really interesting things with these models, such as look at how does it scale with sequence length. So here, you can look at something such as if you make your context length bigger and bigger, even as you're controlling for compute, these Mamba models actually get, so here it's just measuring perplexity. It actually is getting better with longer sequences, even though the compute is still matched. And what that means is indicating that these new types of SSMs both scale, because they scale linearly with sequence length, that means that we pay nothing to just make your sequences longer and longer. And yet we're actually getting better performance because of all this intuition about the selection and so on. It's actually able to leverage the longer context and scale better with sequence length. And so yeah, so these models are still very new, very ongoing, and there's a lot of exciting work to be understood with them. They're good at other types of data such as audio. They scale very efficiently with at both training and inference time. And there's still a lot of ongoing work. So Mamba 2 actually, I won't touch at all in this talk, but we published this a month ago, and it once again advances over Mamba by speeding it up significantly again, and starts making connections between these models, not just to RNNs and CNNs, but also to transformers. So there's a lot of interesting theoretical follow-ups there. And so I'll kind of just leave it there as kind of a teaser for some of the follow-up work, but I'll stop here. So thank you.